Everyone thinks a robot that lifts a car must run on hydraulics, but the newest humanoids prove the opposite. Brake time equals 0. 6 is slash the winning legs deliver 200 Newton meters of torque with 0 leaks because they threw the fluid out entirely. A humanoid leg has to do 2 hard jobs at the same time. It has to hold the whole robot upright without tipping. That's balance. And it has to swing fast enough to actually walk or run. The actuator, the thing that moves each joint, decides everything. Pick one way and your robot is nimble and clean. Pick the other and it's powerful but messy. This is the single decision the entire industry re-argued from scratch. Start with the old way, hydraulics. Here's how a hydraulic leg actually moves. One central pump sits in the robot's torso and squeezes fluid until it's under enormous pressure. Tubes carry that pressurized fluid out to every joint. At each joint sits a cylinder, a piston, and a sealed tube. Open a valve, fluid rushes in, the piston shoves out, and the joint swings. Close the valve and the joint holds. That's it. Pump valves, cylinders, fluid. Why did engineers reach for this first? One reason: force density. A hydraulic cylinder, no bigger than a soda can output staggering torque. This is the machinery that let early Atlas robots do backflips and shove heavy doors open. Pound for pound, nothing beat pressurized fluid for raw explosive muscle. If you wanted a robot that could lift a load or launch off the ground, hydraulics were the obvious pick. The same reason a bulldozer's arm runs on fluid and not batteries. So for years, the most capable humanoids were hydraulic, and it wasn't close. But sit with that setup for a second. Every one of those joints, every burst of force, rides on fluid squeezed to thousands of pounds of pressure. That fluid has to travel through hoses, past seals, through fittings, to reach a limb that's constantly moving and bending. And that raises a question the whole field couldn't dodge. What happens when all that pressure has to run through parts that flex 10,000 times an hour? Here's what happens. Those flexing parts weep, then they burst. This is hydraulics defining failure mode. The exact thing the phrase 0 leaks is pointing at. Think about what you're asking of the hardware. Fluid at thousands of pounds of pressure, forced through rubber hoses, rubber seals, and metal fittings, on a limb that bends with every single step. Rubber under that kind of stress doesn't stay sealed forever. First it seeps a thin film. Then a fitting lets go mid-stride and the leg goes limp, or sprays hot fluid across the lab floor. Anyone who worked on those early machines will tell you the same thing. You spend as much time chasing leaks as running experiments. And leaks are only the headline cost. Run down the rest. The pump is loud. A hydraulic humanoid announces itself from across the building. It runs hot, so you're fighting heat. The plumbing is bulky, eating space inside the limbs. And here's the quiet killer. To hold any pose, the pump has to keep the fluid pressurized. So even when the robot is standing perfectly still, doing nothing, it's burning energy just to stay stiff. A hydraulic robot standing at attention is still working hard. Loud, hot, thirsty, and leaking. That's a lot of baggage for a machine that's supposed to walk into your warehouse. So the field asked the obvious next question. What if you deleted the fluid completely? Delete the fluid completely. That's the electric leg. Here's how it works, and it's beautifully simple. At every joint you bolt an electric motor, a brushless motor, meaning it spins using magnets and coils with no rubbing contacts to wear out. But a bare motor spins fast and weak, which is exactly wrong for a leg. A leg needs the opposite, slow and strong. So right behind the motor sits a gearbox, a harmonic or planetary gearbox, a compact set of gears that trades away speed to multiply force. Spin the motor fast, gear it down hard, and out comes slow, powerful rotation. How powerful? At the hip and knee, where a walking robot needs the most muscle, these joints now hit around 200 Newton meters of torque. That's the number the whole title turns on. 200 Newton meters, enough to drive a full-sized humanoid through a stride, coming straight out of a sealed electric unit no bigger than a grapefruit. Now count what's missing. No pump, no fluid, no hoses, no valves, no fittings. Brake time equals 0, 6 is slash, and here's the payoff hiding in that list. You can't leak a fluid you don't have. The entire failure mode from the last 2 minutes, the seeping, the bursting, the hot spray across the floor, is simply gone. Not managed better, not sealed tighter, designed out of existence. That's the 0 leaks in the title, and it's not a marketing line. It's a direct consequence of throwing the plumbing away. But eliminating leaks isn't why the industry actually switched. The real reason is something the electric motor does that fluid never could. Here's the thing fluid could never do: precise control. This is where electric wins the balance job outright, and it comes down to how directly you can command the joint. In an electric motor, the twisting force is set by the electric current you feed it. More current, more torque. A direct instant dial. And you can change that dial in milliseconds. Better still, you can read the current flowing through the motor, and that reading tells you how hard the joint is pushing. So the motor is a force sensor and a force source in the same part, for free. Why does that matter for balance? Because staying upright is thousands of tiny corrections a second. A gust nudges the robot, a foot lands on a pebble, and the leg has to feel it and push back, right now, over and over. Electric joints can run that feline-correct loop incredibly fast, because commanding and sensing force are both nearly instant. Now put hydraulics next to that. To change a hydraulic joint's force, you have to move a valve and let fluid flow, and that's slower and far less linear. Nudge the valve a little and the response isn't cleanly proportional. Fine feathery control is genuinely harder when your muscle is a column of fluid behind a valve. And this is the insight that flips the whole comparison. A walking, balancing robot doesn't mainly need brute strength. It needs the right amount of force, delivered at the right instant, corrected thousands of times a second. That's torque plus control. And control is precisely where fluid falls behind and current pulls ahead. Now the other half of the scorecard, speed and energy. Electric joints move fast. Spin up a motor and the limb snaps where you want it. But the real prize is what happens when the robot does nothing. Remember the hydraulic pump that had to keep straining just to hold a pose? Electric flips that completely. When an electric leg holds a static stance, it can draw almost no power. A humanoid standing still on electric legs sips electricity, where its hydraulic cousin was gulping it just to stay stiff. Over a full workday, that gap between sipping and gulping decides whether the robot lasts a shift or dies by lunch. So electric is faster to react and dramatically thriftier at rest. Now the honest part, because we don't pretend the loser has no case. Hydraulics still win on one thing, raw peak force from a tiny package. Pound for pound, a hydraulic cylinder can still outmuscle an electric joint of the same size in a single explosive burst. That advantage is real, and it's why fluid isn't dead in heavy industry. But here's why it stopped mattering for legs. Gear a strong motor down hard enough, and you reach the roughly 200 Nm a stride actually demands. You don't need the absolute maximum force fluid can give. You need enough force plus speed plus control plus efficiency. Gearing and smart control closed the practical gap for walking. And once it closed, hydraulics' one advantage stopped being worth all its baggage. So lay the whole scorecard on the table. Speed, electric wins. Instant, snappy motion. Control, precision, electric wins. Command and feel force in milliseconds for real balance. Efficiency, electric wins. It sips power standing still while fluid keeps gulping. Reliability, electric wins the moment you delete the pump, the hoses, and every leak with them. Hydraulics take exactly one box, raw peak force from the smallest possible package. 1 win against 4. Break time equals 0, 6 is slash. That lopsided card is the answer to the question this whole video opened with. Why the entire industry, after building its most famous robots on fluid, walked away from it. For years the wall was torque. Electric joints simply couldn't hit the force a full stride demands. Then gearboxes and motors got good enough to reach that roughly 200 Nm class at the hip and knee. And the instant they did, the last reason to tolerate hydraulics collapsed. Because now you could have the force and lose the leaks, the noise, the heat, and the maintenance bill all at once. That's the switch in one sentence: torque, speed, and zero leaks. The moment electric could match the muscle, its clean, precise, efficient nature won everything else in a landslide. And the fluid drained out of the field for good. Bottom line, a humanoid balances better, walks better, and runs cleaner on electric legs. Because the fight was never about pure strength. It was about controllable strength. But this opens the door you'll want to look through next. How does gearing down a fast motor into a slow, powerful joint actually work without shaking itself apart? And what really happens inside the balance loop that catches a robot before it falls? We'll open that box next.